This is section 4.1, new chapter, and we'll be studying extreme values of functions. And so we're going to be using our calculus to locate extreme values, max, min, using the derivative. All right? Definition, let f be a function with domain D, then f has an absolute maximum value on D at a point C if f of x is less than or equal to f of c for all x in D, and it has an absolute min value at C if f of x is greater than or equal to f of c for all x in D. You do not have to memorize that definition, but it will make sense hopefully as we get started. So just a couple of examples. We have some pictures here, and they have different domains based on closed circles, open circles, that sort of thing. Let me erase something right there. All right, so in this first one, y equals x squared, negative infinity to infinity, has no absolute max, has an absolute min of 0. So the y value is 0, and it occurs at x equals 0. So we want to be sure we can read these correctly. Here's y equals x squared, but the interval, the domain, is from 0 to 2 in brackets. That means 0, closed circle, 2, there's a closed circle there. So there is an absolute max, this piece here, absolute max of 4 at x equals 2, because if you plug in 2 here, you get 2 squared is 4. The absolute min is still at 0. It occurs at 0, and it is 0. This one is different right here because this has a parenthesis at 0. So there's an open circle there. So there's still the absolute max of 4 at x equals 2, but there is no absolute min. This y equals x squared has parentheses on both parts of the interval, so there's no absolute extrema. All right. Now, so this is some more about possibles for max and min on a closed interval from A to B. So on this one, you can have max and min points at interior points of the graph. This one, they occur at the endpoints. From A to B, the endpoints are the max and the min. It could be an interior point and an end point. Here at A, and then up here, we've got a max. Here, minimum at an interior point, max at an end point. So you can have a various combination of that. In this picture, even a single point of discontinuity can keep a function from having either a max or a min value on a closed interval. So this piecewise is continuous at every point of 0 to 1, except at x equals 1. Yet its graph over 0 to 1 does not have a highest point. So if you're looking here, there's an open circle here. These are both closed, but there's no max. So that can happen. All right. The first derivative theorem says if f has a local max or min value at an interior point C of its domain, and if f prime is defined at C, then f prime of C equals 0. All right, so here is the definition of a critical point. An interior point of the domain of a function f where f prime is 0 or undefined is a critical point. All right. We're going to find the absolute extrema using this process. Number one, we'll find all the critical points, and to do that, we'll find the derivative, we'll set it equal to 0, and we'll solve. Then we will evaluate the function at all critical points and endpoints. We'll choose the largest and the smallest values for the max and the min. Let's look at an example. So if the example said, find the absolute max min for f of x equals x squared on the interval from -2 to 1. So the first step, find the derivative of our function. So f prime of x equals 2x. Take that, set it equal to 0, x equals 0. This is my critical point. So on step 2, it said evaluate the function at all critical points and end points. Here's my end points, here's my critical point. I like to kind of put them in order. I have negative 2, 0, 1. And then f of x of those, what that means is I've got to make sure that for these values I plug into f of x. I get 4, I get 0, I get 1. And when you're looking at these values, the largest number is 4, so that's the max. The smallest number is 0, so that's the min. If we graphed that and showed between negative 2 and 1, we have this. We have a max at the end point, we have a min right here in the middle, and we showed that right there. Okay, so that's what we're going to be doing. Let's go look at our problem set. All right, number 1 and number 2 are just analysis questions. There's really not any work to do. Determine from the given graph whether this has any absolute extreme values on the interval from A to B. And so here is our graph. Here is A, here is B, and it says, do we have any absolute maxes or mins? It has an absolute max at x equals C2. That's right there. So there's our max. And at x equals b, that's our lowest. So you could check these others. They will not work. That is the one that is true. Explain the results in terms of the extreme value theorem. And we could go back to the notes. You might go back and look at that again. Since the function f is continuous on the closed interval, it says we will have both an absolute max value and an absolute min on the domain. So that is related to the extreme value theorem. Let's look at number 2. All right, here is our interval from A to B, and we notice there's some holes there. So do we have an absolute max or an absolute min? We do not. So we're choosing D. The function does not have any extreme values on its domain. And then again, we are explaining the results in terms of the theorem. Since the function f is not continuous, note the holes, and the domain is not a closed interval, f may or may not attain any absolute extreme values on its domain. All right, let's go to 3. On number 3, find the max and min values on the given interval. So our interval is negative 1 to 2 inclusive, and here is our function. So you take your function, find the derivative, set it equal to 0. X equals 0 is my critical number. And I didn't put this in a table, but f of 0, f of negative 1, f of 2. I'm going to do that. It means I'm plugging them in the original here, not in the derivative. And here are my y values. The largest is 1, and the min is negative 3. So negative 3 here, 1 here. Number 4. So f of theta equals cosine theta on the interval from negative pi to pi over 4. All right, so we take our function here, we find the derivative, which is negative sine theta, set that equal to 0, and that gives us that theta is equal to 0 because sine at 0 is 0. So we have to evaluate it at 0 in the original and at the ends of the interval, negative pi and pi over 4. And you get 1, negative 1. This is square root of 2 over 2, approximately 0.7. So the absolute max is 1, and that occurs at 0. The min is negative 1, which occurs at negative pi. And then if you want to pick the correct graph, you could graph cosine theta, and you could set your window at negative pi and pi over 4, or you could go, I mean, this goes a little further, but this is what you would get if you if you graphed it. When you graph it on your calculator, let's see if we can get that up for you and show you. So I have put the original in here, y equals cosine x. I made sure on mode that I was in radian because I wanted to use pi over 4 and negative pi for my window. I went to my window and this is negative pi. If you can just put it in as negative and second and the caret key right there is pi. It will, when you hit enter, change it to decimal. And this is pi over 4. I also matched the range, so I made the y min -2 and the y max 2. And then when you hit graph, we do see this part here. And you're getting it literally from here to here. So you can tell that it is not the other two. So if you want to do that on your calculator, you can do that, or you can just check to see if it matches what you've got. All right, let's go to 5. On 5, there should be, it's f of x is equal to x to the 8/3. I don't know, that didn't come through on the paper. Oh, oops, that was bad. Let me see if I can make that work. Okay, and the interval is from -8 to 8. So f of x is x to the 8/3. Find the derivative. The derivative is 8/3 x to the, take 3/3 away, that's 5/3. When you set this equal to 0, you've got x to the 5/3. Divide that over, you still got 0. And here x is 0. So that's your critical number. Then you're going to evaluate -8, 8, and 0. You can do that in the calculator. -8 to the 8/3 is 256. 8 to the 8/3 is also 256. And 0 to the 8/3 is 0. So the absolute max has a value of 256. Both of those did. And the min is 0. So that's how you're doing that one. And same process again. Number 6, you're not asked to find the max and the min, you're just asked to find the critical points. Again, here's your function, find the derivative. That's 2x minus 2, set that equal to 0, you get x is 1. That is the critical point. If there's more than one, you would list those. Number 7, find the extreme values of the function and where they occur. So we know we've got a parabola. Y equals 4x squared plus 5x plus 1. Derivative, y prime equals 8x plus 5. Set that equal to 0. You get x is -5/8. And we don't have an interval, so if we're going to test, here's what we can do. We can draw a line, put a hash mark for any critical number. X is -5/8, and we're on this side of the critical number and this side of the critical number. You can test to make sure, like if you tested, this is like 1 and 3/8. So if you did -2 in the derivative, if you put -2 here, you would get a negative number. So that's negative. If you put +2, you're going to get a positive number here. And so what you're saying is, on this side of the critical number, we're decreasing, and on this side, we're increasing. So at -5/8, we have a min. We can see it right there. If we plug -5/8 into the original right here, we get -9/16. This is the min. So here is our answer, a minimum value of -9/16 at x equals -5/8. But we could see it, we saw that it's a min, and then we had to come up with the value of the min. All right, number 8. Y equals 2x over x squared plus 1. The thing here is we got a quotient when we find the derivative. So we'll do that like we've been doing, go through your roadmap, do all of this, and you end up with this. You're going to take that derivative, set it equal to 0. It's okay. This whole piece multiplies to the other side and still have 0. So we have 2 minus 2x squared is 0. Subtract 2, then divide by 2, and you end up with x squared is 1. So x is plus or minus 1. And f of 1 is 1. F of negative 1 is negative 1. And not sure where we get to put that in the answer. So we had to put both of them in, and we said that the max is at 1, 1. So we'll have an ordered pair here of 1, 1, and the min is at negative 1, negative 1, and that will be an ordered pair here. Then number 9, when we updated to the new edition of the book, could not find this particular question again, so that one's gone, so you don't have 9. We do have number 10. Find, let's see, the function v of x is equal to this. This looks like it's cubic, and you have an interval from 0 to 5, not including 0 and 5 because there's no equals there. Find the extreme values and interpret. All right, so we'll go down here. V of x equals this. Before we take the derivative, we want to go ahead and multiply this out and then multiply that by x. So here is my multiplied out function. V prime is 160 minus 104x plus 12x squared. So I'm going to take that and put it equal to 0. Now, I notice that it looks like all three of these terms are divided by 4, or could be. So I do that first, and I have 40 minus 26x plus 3x squared. I like, when I factor it, I turn it around. It's what makes sense to me. And this is going to factor with 3x minus 20 and x minus 2. That's going to give us a 20x, negative 20x, and a negative 6x. So that's negative 20x. And it's going to give us a negative, positive 40 on the end. So that works. 3x equals 20. So x is 6 2/3. We know that's not in our interval. That one's discarded. And then x equals 2. That is the critical number. If you plug in 2 into the original, right up here, then you can get 144. So plug in f of 2 into your original, and you will get that. Now, so how do we put that in? So the extreme value is 144. The value found in the previous step represents the largest volume of the box and occurs when x is 2. So that should get us on the extreme values.